NanoHub U, online instruction.
Welcome back to Unit 2 of our course. This is the 7th lecture. Now, in the past lectures, when we were setting up these NEGF equations, one of the things I stressed is this picture of inflow and outflow. That is, there's this inflow and there's this outflow, and if you want the current at some contact, you can look at the difference of the two. Now, what we'll be doing in this lecture is I'll be giving you an alternative expression for current, which you will obtain starting from this. And the reason I hadn't quite done this before is that this expression is not general. It only applies under a certain limited set of circumstances. Okay? And I'll try to explain what it is. But it leads to this important concept of transmission, which is widely used in the mesoscopic literature and in nanoelectronics. And so I wanted to connect to that. Now, the first point is that in these contacts, which are described by a Fermi function, there is this basic requirement, which we discussed earlier, that sigma n should be related to gamma, which is the anti-Hermitian part of sigma, by sigma n equals gamma times f. Similarly for contact 2. Now, if this is true, then you see you could take our expression for current that we had before, which comes from subtracting outflow from inflow. You get that expression. You could replace the sigma n with gamma f and thereby get this expression for current. It's trace of gamma 1 times A F1 minus Gn. Now this, though, is not generally true. This is the one that is generally true. This is only true when sigma n1 is equal to gamma 1 times F1. And when is this true? Well, whenever your contact is actually described by a Fermi function. So for example, I've stressed the importance of including this sigma 0, and later in this unit we'll talk about it more, which describes the interaction with the surroundings. And that in general would not be described by a Fermi function. Now, but let's for the moment forget that and assume this is true so that the current is given by this expression. And we'll now proceed to do a little algebra to put it in the form of this transmission formalism. So we have this AF1 minus Gn, and we need to simplify that. So first thing is we start with the expression for Gn, which is Gr sigma n Ga, and sigma n has two parts, the sigma n due to contact 1, sigma n due to contact 2. And of course we are ignoring any other, these dephasing contacts. That is, we are assuming the contacts are described by this Fermi function, and that's all, and there are no other contacts. So we write it this way. A is Gr gamma Ga, that's an identity we discussed earlier, and the gamma is gamma 1 plus gamma 2. So if you want to write A times F1, you'll have gamma 1 F1 plus gamma 2 F1. What we need is the difference between the two. So when we subtract this from this, you'll notice the first term cancels out, and the second term gives you Gr gamma 2 Ga times F1 minus F2. That's this. So now you can write the expression for current as trace of gamma 1 Gr gamma 2 Ga times F1 minus F2. Now I should remind you once that we are generally writing this current through a range of energy dE. So this is like current per unit energy. And if you actually wanted the total current, you should integrate over all energy. Right? But in general, I won't be writing this integral. And you should remember that what we are writing is the current per unit energy around a given energy. Okay. Now, this is then what is called the transmission from contact 1 to contact 2, between the two contacts. Now, this is actually more general. You could apply it to multi-terminal devices also. That is, if you had a device with many terminals, but they are all described by this rule, namely that sigma n is gamma times f. And I should mention in this context that there is a widely used method for including dephasing due to Boutiqueur, where you, instead of this sigma zeros, what you imagine is as if there's another contact there. But you assume that that contact is also described by its own Fermi function. Right? Whereas what we'll be using is the NEGF method, where we do not assume that these are described by a Fermi function. I believe that the NEGF method is more versatile, but the Boutiqueur method is widely used, and there you usually think of it as another terminal but described by a Fermi function. And the expression we'll now be obtaining applies as long as your contacts are described by Fermi functions. Okay. So if this is true, now we can start from our usual expression for current. That's obtained by subtracting outflow from inflow. And this is an expression that holds in general. But what we'll be doing after this assumes this relation, and so is not generally applicable. So if you use this, I guess instead of sigma, you have a gamma times f, so you get AFP minus Gn. How do you get AFP minus Gn? Well, if you look at Gn, is Gr times gamma 1 f1, gamma 2 f2, etc. If you look at AFP, well, A is Gr, gamma 1 plus gamma 2, etc. If you multiply by Fp, you get a Fp everywhere. So if you look at these two terms, AFP and Gn, and we need the difference, you'll notice each term is similar. They all involve Gr, gamma 1, Ga, Gr, gamma 2, Ga. But in this expression, every one of these Fs is Fp. But here it's F1, F2, etc. So when I subtract the two, you see what I get is Gr, gamma Q, Ga, Fp minus Fq, where Q runs from 1 to however many terminals you have. So if you put Q equals 1, you get the difference of the first two, these two terms. If you put Q equals 2, it's the difference of those two, and so on. Now if you take that expression and put it back in here, you'll get this general expression for current in a multi-terminal device. And those of you who are familiar with the Boutiqueur equations, which we briefly discussed in part A, will notice the similarity. That is, what appears here is what in the Landau-Boutiqueur formalism would have been called this transmission, PQ. Okay? And the reason it's called transmission is that this quantity can be interpreted in terms of the probability that an electron can transmit from one contact to another. And in the rest of this lecture, I'll try to explain this point. And for this point, let us consider a simple example. We have a 1D wire, and if you took a course in quantum mechanics, one of the first things you learn is how to calculate the transmission through a barrier, through a potential barrier. And we are assuming a very sharp potential barrier, like a delta function. That simplifies the algebra a little. So you have a U0, a delta function at z equals 0. You have an incident wave, a reflected wave, and a transmitted wave. And one of the things you do in elementary quantum mechanics is you try to use the continuity of wave functions and their derivatives to calculate the reflection and transmission. And what I'll show you is that by using our expression based on the NEGF method, you'll get the same answer that you would have got if you had done it the usual way, the way one does it in quantum mechanics. Now, what we'll be doing though is the problem not with a continuous spatial variable z, but a discrete version of it, where you have a discrete lattice. So z is actually an integer n times the lattice spacing a. So you still have incident wave and a reflected wave and a transmitted wave. And this is a discrete lattice. Diagonal elements are epsilon. The connecting elements, the upper diagonal and lower diagonal elements are t. One tricky point, when we go from the continuous to the discrete, this delta function, note that this is u0 delta z. What you should put here is u0 over a, the potential. Because here, because it's a discrete lattice, your width of this is like a. And the definition of a delta function is something that's infinitely tall but also infinitely thin, such that the area under the curve is 1. In a discrete lattice, of course, the thinnest you can get is a. So in order to have an area of 1, the height needs to be u0 over a. so that the area under the curve would be equal to 1. Okay. That's the delta function, and of course you want the area under the curve to be u0 because it's u0 times the delta function. Okay. Now what we'll show then is we'll apply our method to calculate this transmission using the Green's function method, and we'll show you that you get the usual answer. That is, you'd obtain for transmission through a scatterer, which is given by h bar v, the velocity, square divided by this u0 square plus h bar v square. So how do you do that? Using the Green's function method? Well, the way it works is, takes this discrete lattice, and in general, if I was doing this numerically, I might have say 10 points in my lattice, so all my matrices would be 10 by 10. But for this problem, because it's a delta function, it just involves 1 point. So I could just take that point as my device and represent the rest of it here in terms of a sigma, rest of it there in terms of a sigma. So you see, if my device had 10 points, then H would be a 10 by 10 matrix. And I'd be dealing with matrices that were 10 by 10. And for that, usually it would be kind of inconvenient to do it by hand. But on a computer, that's nothing. Computers, 1000 by 1000 matrix is no big deal, really. And so for numerical simulation, you just write down the matrices and get the computer to evaluate it for you. But if you want to do it on paper, then it's good if the matrices are 1 by 1, maybe 2 by 2. Okay? And for this problem, we can use a 1 by 1. There's just 1 point. The diagonal element is ordinarily epsilon, but because there is a barrier of height u, it becomes epsilon plus u. What's sigma 1? We discussed in the last lecture. It's t to the power I k a. Sigma 2, that's also t to the power I k a. Remember, these are also 1 by 1. So usually sigma 1 is t to the power I k a on 1 point and zeros everywhere else. But this is just a 1 by 1. There's only 1 point. So it's just t to the power I k a. What's gamma? Well, that's I sigma 1 minus sigma 1 dagger. And as you have seen, that gives you this 2t sine ka minus 2t sine ka, which you can write as h bar v over a, like we did in the last lecture. The gamma 2 is also h bar v over a. So now we are ready to evaluate the transmission, gamma 1, gr, gamma 2, ga. We have gamma 1 and gamma 2. We need this Green's functions. So how do you get the Green's function? It's E minus H minus sigma inverse. So that's E minus H is epsilon plus U, minus sigma is sigma 1 plus, and sigma 2. This is t to the power I k, that's also t to the power I k. So minus 2t e to the power I k. Now e to the power I x is cosine x plus I sine x. So if I spell that out, I'll get 2t cosine ka plus I sine ka. Now you'll notice here that because we have the dispersion relation in the leads, that E is equal to epsilon plus 2t cosine ka, that means this E minus epsilon minus 2t cosine ka, that just is 0. It cancels out. So what you're left with then is minus u minus 2it sine ka. And 2t sine ka minus is h bar v over a. So you get minus u plus I h bar v over a. So that's the Green's function. So if you put all that in, then your transmission involves these 4 terms, and we just calculated gr. So if you write it out, the gamma 1 is h bar v over a. We just calculated gr, that's gamma 2, and ga is just the conjugate of that. This is 1 by 1, so I don't need to worry about transpose. So that's the conjugate. When you multiply it out, you get h bar v over a square, u square plus h bar v over a square. Now remember, the u is related to the strength of the delta function u0 by u0 over a. So if you put that in here, then all these a's will cancel out, and then you will have this result. And this is a standard result you could have obtained directly by solving the Schrodinger equation with a delta function potential. But the bottom line of all this is that this t bar, which came from our Green function method, you see, it can be interpreted as this transmission through a barrier. That as if your device is some kind of a barrier, and what you're calculating is the transmission from left to right. Now, I should point out though that this transmission probability here, this transmission here is actually, in general, it is the number of channels in your conductor times the probability. So let's say you have 10 channels and the average probability is of an electron to get through from left to right is 0.2. Then this quantity would have been 10 times 0.2, which is like 2. Here, because we are using a one-dimensional wire, of course, this quantity itself is the transmission probability. Okay? But in general, if you had many channels in the wire, so if it was a two-dimensional wire, then you see that number could, in principle, what you calculate here could even be bigger than 1. Okay? Now, so if you plot this out then, so it's like you have this one-dimensional wire. What we had seen in Unit 1 is the EK relation, which was obtained by assuming periodic boundary conditions. And what we have now calculated is the transmission as a function of energy. Now, if U is 0, which means there's nothing here, no barriers, then of course you have a ballistic wire, and in that case the transmission is 1. 1 across the band, that is from the bottom of the band to the top of the band. Once you go outside the band, it's 0, because then there's no states. But the transmission is exactly 1 here, and that comes from this expression. If you put U0 equals 0, that's it, it's 1. On the other hand, if you put a U that's, let's say, equal to, so that is equal to 2 times T, then you can see the transmission goes down. And it goes down by different amounts at different points. Why? Because how much it goes down depends on the velocity. And the velocity varies along the EK plot, because the energy is epsilon plus 2t cosine Ka. So the velocity goes as sine Ka. So the velocity is 0 here, where Ka is 0. It's also 0 here, where Ka is equal to pi. It's a maximum right in the middle, where Ka is pi over 2. So the maximum value of this velocity is like 2t. So that's why right around there, that's where the transmission is the biggest, because that's where h bar v is biggest. So it all follows from that expression. So this then gives you a feeling for how to connect what we did based on this Green's function method, to the scattering theory and this transmission formalism that is widely used. So to sum up here then, basic point is that when you calculate currents, this is a very general expression that is generally applicable. But then you can write the current in this form in terms of a transmission easily if sigma n is related to gamma through a Fermi function. And that holds if your contacts are described by a Fermi function, may not hold for, let's say, this interaction sigma, because there you cannot assume in general it's a Fermi function. So if you assume that, then you can write it in this form, and this is a form that is widely used. Now, in general, of course, as I mentioned in part A, you can always write the current in terms of F1 minus F2 times something. So in principle, I could have used this expression to find the current, divided it by F1 minus F2, and found an effective transmission. That you could always do. It is just that if these things are not described by a Fermi function, I won't have a simple expression like this for transmission. So what I should do is still, if I really want current, I should use this. And then if I really want to find a transmission so I can compare with other things, then I should take whatever current I get and divide it by F1 minus F2. Okay? And remember, here I've explicitly shown the integral over energy. By and large, I have not been doing that. Here, for example, this is current per unit energy, and it's understood that we should have an integral over energy on this one as well. Okay. And so this is what I tried to illustrate with this 1D example, a simple 1D example with a barrier. This is a very instructive one to go through because, you see, we have the general equations that we did in the first part of this unit. What we now want to do is look at different examples to get a feeling for how to apply the method, how to apply these equations. And we have kind of done the simplest of these, which is the one barrier. In the next lecture, we'll do two barriers. Thank you.